Well, hello and welcome to week 12, where we're going to be doing what's usually called U substitution, but in general substitution, and then a few more differential equations. So first of all, with the U substitution. So it's all about the chain rule. So let me just start with a function, and let's say that it's 8x plus 7 is raised to some power to the fifth. And we're finding the derivative. So at first you just do the power rule, the 5 goes in front and you multiply. For now, the 8x plus 7 stays the same. And then subtract 1 from the exponent, so now it's raised to the fourth. And then the other part of it is the chain rule. So now I need the derivative of the inside, and the derivative of 8x plus 7 is an 8. So multiply by 8. And usually I would combine these two and just put a 40 in the front, but I'm trying to make a point about the chain rule. So if you then are doing the antiderivative, and let's say that it's just an 8x plus 7 to the fourth. So basically this part's missing and this part's missing. And at the end, I do need to say that the variable is x, so this should say dx. So in other words, find the antiderivative. So basically, when I take the derivative, I go from this to this. When I'm doing the antiderivative, I'm going from this to this. So to find the antiderivative, I would add 1 to the exponent, which is why I've got a red pen. And then that's a 5. And then divide by 5. So that means that it would be 8x plus 7 to the fifth over 5. And then the thing that's missing is the 8. So there is no 8. I do have the number 5. It's in the wrong spot because it was supposed to be in front, but we could deal with that later. But there's no 8 at all. So this answer right here is not correct. So there's something else we need to do. So basically, what's missing? Why is this not correct? Yes, there is supposed to be a plus c, but that's not what I'm talking about. What I'm talking about, this is completely missing the 8 that this one had. So that's the U substitution. So if I start over and I say, find the integral of the 8x plus 7 raised to the fourth, and then dx. So I'll let the inside be replaced with another variable, and then that's usually u, which is why we usually call it U substitution. So you let u equal the inside part, and that's going to be an 8x plus 7. And then the derivative of that would be an 8. So the derivative of 8x is 8, the derivative of 7 is 0. And then I would, just like with algebra, multiply both sides by dx. So these cancel, and I get du equals an 8 dx. So basically that's the 8 that was missing. And then I need another page, sorry about that. And then I look at this problem and say, well, does this original problem have an 8 dx? No, this one was missing it. So actually, I'm going to have to make this part and this part match. And since this one was missing the 8 and only has dx, I need this one to only have dx. So I need to get rid of the 8. So multiply both sides by 1/8 or divide both sides by 8. And these cancel. And now this is just what dx equals. Dx right here is going to get replaced with 1/8 du. And this part inside the parentheses is just going to become u to the fourth. So then I would have integral. This part is u to the fourth, And then dx gets replaced with 1/8 times du. And when you're doing antiderivatives, if you have multiplication or division by a number, you can actually factor that out. So I would factor out the 1/8, and then I would say find the antiderivative for the u to the 4th. So another goal of u substitution is you take a problem that's more complicated and you turn it into something simpler. Because with this one now, all we need to do is add 1 to the exponent and then divide by that number. So add 1, and that would be a 5, and divide by 5. And this could be factored out so that when you multiply these two, that's going to be 1/40th. And then it's going to be u to the 5th, and then plus a c. And now we're done with the calculus part. The only thing I need to do is replace the u with what the u equals. So replace the u with an 8x plus 5. So the 1/40th would stay there, and then I would put parentheses, the 8x plus 5, no, sorry, that was 8x plus 7, is raised to the 5, and then plus c. And then it's done. So that's the idea of u substitution, and now we're going to do a few more examples. So for the next example, find the antiderivative for the square root of 5x plus 1 dx. So the guiding principle with what you let u equal, it's going to be the inside part. Because just like the chain rule, you have to take the derivative of the inside. So this is basically much like the chain rule. So you let the u equal what's inside the square root, and then take the derivative. So it's going to be du dx, and the derivative of 5x plus 1, that's just a 5. And then do the algebra step that you separate the variables, because I want all x information to be on the right, and I want all u information to be on the left. So the left side is just going to say du, and the right side is going to say 5 times dx. And when you look at this dx, it does not have a 5 multiplied with it. So for this one, I need to eliminate this 5. Whenever you get to this step right here, you can only multiply or divide by a number. You can't do anything with variables, and you can't add or subtract, you can't square root. All you can do is multiply or divide. So multiply by 1/5 on each side so that these cancel. And now it says the dx right there is going to get replaced with 1/5 du. And this part is going to get replaced with u. So it becomes integrate the square root of u and then 1/5 and du. So once again, it takes something that's more complicated and makes it simpler. Now, before I find the antiderivative, I'm going to do two things. One, this is a constant that's being multiplied, so that means I could factor it out. The other thing is with u to the square root, you can rewrite that as u to the 1/2. And then do the antiderivative. So add 1, which is going to be 3/2, and divide by 3/2. Well, when you divide by a fraction, that actually means invert it and multiply. So there was already the 1/5 on the outside. Then invert this fraction so it becomes 2/3. And then this part is going to become u to the 3/2. And now that we've done the antiderivative, just put a plus c. There's just a tiny bit I need to do, and that is the u is equal to a 5x plus 1, so replace the u. And also this will be 2/15. So that my final answer is 2/15. And then replace the u with the 5x plus 1. to the 3/2 and then plus c. So the good thing about finding antiderivatives is that you can always check your answer, which I'm going to do right here. So if I take this and I find the derivative, then it should be that square root of 5x plus 1. So basically taking the derivative will undo the integral and give you back the original problem. So if I take the derivative of my answer, 2/15, 5x plus 1 is raised to the 3/2 plus c. Then do the power rule. So the 3/2 goes in front and multiply. And then subtract 1 from the exponent. So this is going to be, well, actually I could have the 2's cancel on the top and the bottom, and then the 3 will divide into 15, which is actually just going to leave 1/5. And then the inside part will stay the same. And then 3/2 minus 1 is 1/2. And then the derivative of, the derivative of the inside is 5. So because of the chain rule, I need to multiply by 5. And the derivative of c is 0. And once I have these cancel, I can rewrite this as square root. And it worked, because when I did the derivative, it gave me the original problem back again, the square root of 5x plus 1, the square root of 5x plus 1. So now I'm confident this one deserves 2 check marks. So if you've got parentheses, the u should be what's in the parentheses. If you've got a square root, the u should be what's in the square root. If you've got a fraction, then the u should be the denominator. So let u equal 6x plus 1. And now take the derivative. So du dx, the derivative of this is just a 6. And then this step is always the same. Multiply both sides by dx. So basically I have only the u information on the left, and I have the x information on the right. And this one said it's 1 times dx, not 6 times dx. So I need to eliminate that 6, either divide both sides by 6 or multiply by 1/6 on each side. So in the substitution, this is going to become du over 6, and this is going to be 1 over u. So I've got integrate 1 over u, and then du over 6. And this comes from the derivative of natural log. So somebody had the natural log of u, and then they took the derivative of it and got 1 over u. So that means this one is natural log of u. And then it's still divided by 6, so it's still divided by 6, and then put a plus c. And as always, the last step is replace the u with whatever u equals. So this one's going to be the natural log of 6x plus 1 divided by 6 plus a c. And by the way, sometimes this answer is given as natural log the absolute value of 6x plus 1 divided by 6 plus c. And the reason for that is you can't take natural log of a negative number, so the absolute value would get rid of the negative. Personally, I just use the parentheses, and then I just remember that you can't take natural log of a negative. But either one would be acceptable. And then for the next example, let's see, this must be number 4 already. What if it's the integral of a 2x times 1 over 1 plus x squared? So when you've got a fraction, it's good to try letting u equal the bottom part. Now with u substitution, sometimes you try it, and the first time it doesn't work. But if you go with the first idea that u equals what's inside, either what's inside the parentheses, what's inside the square root, or what's in the denominator, that works most of the time. And then take the derivative, and the derivative, that's going to be 0. The derivative here is going to be 2x. And then, oh, I accidentally wrote du because I was in the middle of talking, didn't pay attention to what I wrote. And then multiply both sides by dx. So these cancel. On the left side, it just says du equals 2x dx. And if you look at the original problem, it has 2x times dx. They're not written right next to each other, but it is still multiplication, so it still is 2x dx. So this problem could have also been written, because this is 2x times 1, it could have been written as 2x over 1 plus x squared dx. And then right there is the 2x dx. So for this one, I don't have to do anything. All I do is make the top a du. So the top becomes du, and the bottom is the u, so it's du over u. And that is just like the last one. So for the du, you could also say that it's 1 times du, and that way this is 1 over u, and that means that it's natural log. So the antiderivative of 1 over u is the natural log of u, and then plus c. And like on all of them, then replace the u with the 1 plus x squared. So my final answer is natural log 1 plus x squared plus c. And then for example number 5, the variable does not have to be x. Let's say that it's t to the 5th, and then 7 plus t to the 6th. The whole thing is raised to the 9, and then at the end would need to be a dt, saying that the t is the variable. So whatever's inside the parentheses, that's a good thing for the u. So let u equal the 7 plus t to the 6th. And take the derivative. So du, oh, look at the mistake I just made. I'm so used to using x. This is not an x, this is a t. See? All right, so the variable is t. And the derivative here would be 6t to the 5th. 6t to the 5th. And then I only want the du on the left side, so multiply by dt and multiply by dt. Cancel. And then this one says you need a 6t to the 5th and dt. Well, we have t to the 5th and we have dt, but we don't have a 6. So multiply both sides by 1/6. That's going to cancel this 6, leaving us just t to the 5th dt. And this problem has t to the 5th and dt, so those t to the 5th and dt are going to get replaced with 1/6 du. And the 1/6 is the constant, so you could even factor it out into the front of the integral symbol. And then when I write 1/6 and du, that already takes care of this and this. So they got replaced with 1/6 du, 1/6 du. And then this is going to be u to the 9th power. And then we're ready to do the antiderivative. So add 1, which is a 10, and divide by 10. When I put this one and this one together, that makes 1/60th. and then it's going to be u to the 10th power plus c. And like always, then replace the u. So the 1/60th can stay there. Replace the u with 7 plus t to the 6th, and then it's to the 10th. Okay, now we have a couple of examples that take just a little more algebra. So for example number 6, what if you integrate x and the square root of x minus 1? And this one I got directly from the homework, but that's fine too, because I usually do an example very much like this when we do u substitution. So you let u equal what's inside the parentheses. So let u equal x minus 1. And when you take the derivative with respect to x, the derivative of x is just a 1. And then separate the variables. So on the left side is just the du, and on the right side is just 1 times dx, so that's dx. So that means this gets replaced with u, so this is going to become the square root of u. The dx and the du are the same, so this is going to become du. But once I have this as du and this the square root of u, I can't have an x in there. So when you do u substitution, you change everything from x's to u's. So that's why this one requires a little more algebra. So because of this extra x, I need to do some algebra right here and solve for x. So in order to do that, just add 1 to both sides, and that's going to leave u plus 1 on the left side. And then that means that extra x gets replaced with a u plus 1. So it's going to be integral, and then in place of this x goes u plus 1. This is going to become the square root of u, and this is going to become du. All right, we need to do a little more algebra before we can do the antiderivative. So the next thing to do is rewrite u as u to the 1/2 power. And then the next part of the algebra is distribute. So this u is really u to the 1, and when you multiply by u to the 1/2, then you add the exponents. So it's going to be 1/2 plus 1, which is 1.5, or also known as 3/2. And then when you multiply this times the 1, it's just going to say plus u to the 1/2. And then all of that is times du. Okay, we're almost done with this one. So if you add 1 to the exponent, 3/2 plus 1, that's 5/2. So divide by 5/2. When you go to the next one, add 1, and this is 3/2, and then divide by 3/2. And when you divide by a fraction, that means you need to invert and multiply it. And then go to the next one and invert and multiply. And then put a plus c. So now we're done with the hard part. The only thing left to do is u equals x minus 1. So replace this with x minus 1 and replace this with x minus 1. And we're done with example number 6. And then this one is done. Okay, I want to do just one more example before we go on to differential equations. Example number 7. What if it was the integral of 1 over x times natural log of x. So when you have a fraction, you usually let the u equal the bottom part, but I'm going to get a scratch piece of paper right here and just show you why that doesn't work on this particular example. So if I let u equal the x ln of x, and I let it equal the whole bottom part, then take the derivative. So this is a product, so you need to use the product rule. The derivative of x is a 1, and then leave natural log of x alone, plus, now leave x alone and take the derivative of the natural log of x, which is 1 over x. And for one thing, u substitution is supposed to make things easier, and this is not easier than the original problem. The other problem is, once I multiply both sides by dx, I would have the natural log of x plus, here I could reduce, this just becomes a 1. So that means in the problem, I would have to have this. I would have to have the natural log of x plus 1 times dx. All I have is a 1 times dx. This is way too complicated. So that's an example of what I was talking about, u substitution. There's certain guidelines, but sometimes you try something and it just doesn't work. So you just throw that one away and start again. So what I'm going to try next is let u equal just the natural log of x, because that way when I do the derivative, I don't have to do the product rule. Also, when I do the derivative, it's going to give me something simpler, because the derivative of natural log of x is just 1 over x. Not only is it simpler than what I just tried last time, but also 1 over x is sitting right here in the problem, which is perfect. So this u substitution is going to work. So this step is always the same. You take the derivative, then multiply both sides by dx so that these cancel, and the left side just has du, and the right side has 1 over x times dx. And this one has 1 over x, and this is an implied multiplication, so it has 1 over x and it has times dx. So this is perfect. So that means that these two that I just circled, these two get replaced. So you're taking something more complicated and you replace it with just a du. And this just becomes a u. So that means that on the top, all of that gets replaced with just du, and that takes care of this and this and this. It gets replaced with just a du, so it's definitely simpler. Then on the bottom, there's this natural log of x, and that's what u equals. So this definitely became simpler because this came from the derivative of natural log, so the antiderivative is the natural log of u, and then plus c. And then replace what u is equal to, so that means that it's going to be the natural log of the natural log of x plus c. All right, now on to the second half of today's show, and that is differential equations. So basically, instead of using the integral symbol and say find the antiderivative of x squared dx, and then you say, oh, the answer is add 1 to the exponent, that's a 3, and divide by 3. So that's going to be x to the 3 over 3, and then put a plus c. So that's one way to write integrals or antiderivatives. The other way is someone would say the derivative of something equals x squared. What was the function that somebody took the derivative of? And it's a different way of writing it, but it would be the same work. So the antiderivative of x squared would be add 1 to the exponent, divide by that number, and then put a plus c. Now, there is one question in the homework that says, what's the order of a differential equation? So the order is the highest derivative that appears. So for example, this one is a first, because that's the first derivative, first order differential equation. If it had y second derivative plus the first derivative plus the function equals x, then because the highest derivative is 2, the second derivative, then this is a second order differential equation. And then this has lots of applications in physics and engineering. At this point, we can't do any of these more difficult ones, but they do ask a question about that in the homework, so I thought I'd bring that up real quick. Okay, then on to example number 8. Suppose that dy dx equals 12x. So like I said, this and this are basically the same question, but just written in a different way. So this one is basically saying, so what if y prime equals 12x, then what does y equal? So with 12x, you could look at the x as x to the 1. So when you add 1 to the exponent, that's going to become a 2, and then divide by 2. And this could actually be reduced because 12 divided by 2 is 6. So it's going to be 6x squared and then plus c. And if they give us any extra numbers to plug in, I could plug in the numbers for x and y and find out what c equals. With this one, there were no numbers to plug in, so it just has the plus c. Next, example number 9. So suppose you have dy dx equals x. All right. Now compare that with, what if it said dy dx equals y? So this one is basically just like what I just did, except this one had a 12 in it, this one does not. So basically I could do the exact same work as the last example, and I would get x squared over 2 plus c. But there is a different style, and that different style really is going to help when we go to do this one. So what you do is, just like with u substitution, you separate the variables. So you multiply both sides by dx, and after these cancel, it's only going to say dy equals x times dx. So this is called separating the variables. The y information is on the left, the x information is on the right. And then you just say, find the antiderivative on both sides. Well, the antiderivative and the derivative, which is what d stands for, so the antiderivative and the derivative cancel each other out. It just gives you y. And then finding the antiderivative here, you would just add 1 to the exponent, that's a 2, and divide by 2. So this is going to become x squared over 2. And now that I'm done with the antiderivative, put a plus c. Now compare that with this one. So this one has some y information on the left side and some on the right side. And whatever the dy or the dx is, I want that to be on the top and on the top, and separated. X is on one side, y is on the other side. So I'm going to move this y to the left by dividing. So divide by y and divide by y. And I'm going to move this dx to the right by multiplying. So multiply by dx and multiply by dx. So these are going to cancel, leaving dy over y. these are going to cancel, leaving just 1 dx. So now the y information is on the left, the x information is on the right. And then that's when we do the integral on each side. So then integrate this side and integrate this side. Well, this one right here, if you look back to the first 3, 4, 5 examples that I did, this showed up several times. This is from the natural log. It's basically 1 over y, so that would be the natural log of y. And the antiderivative of 1 is just an x. And we're now done doing the antiderivative, so I can just put a plus c. And then this one has one more step because I do need to solve for y. So in order to eliminate the natural log, you use e, and then these will cancel each other out, and it leaves y equals e raised to x plus c. All right, so we're done with that one. One other note is you can use the rules from algebra to rewrite this one as e to the x times e to the c. Because when you multiply, that means that you add the exponents. So you could leave the answer like this. You could also put the answer like this. And for example number 10. So this is going to be a fast one, and this is similar to the homework, although it's a traditional type question. If you were given the answer, can you check and make sure that it's right? So is this the answer? So in other words, instead of us having to do all of this work to get the answer, they're already telling you what the answer is. Is y equals 5x a solution to the differential equation dy dx equals y divided by x? So with this one, we do not have to separate the variables and then integrate it and then solve for y and all of that. They're just saying, is this the solution? So on this side, they have the derivative. So we need to first find the derivative. All right, dy dx. The derivative of 5x is just 5. And I know that y equals 5x. So I can plug this in for dy dx on the left side. I can plug this in for that y on the right side and then see if they're equal. So there on the left side is going to be dy dx gets replaced with a 5. And does it equal? So right now it's still a question. On the top is y, so replace that with 5x. And on the bottom, they just have the letter x. And then, are these equal? Well, yes, because after you cancel the x's, it says, does 5 equal 5? And that is true. All right, just one more. Just one more. So, for example, number 11, when we did things with money and we used the PERT formula, we could say, so this is about money, invest money. A equals the amount of money in the account. And it says that the derivative of the money in the account over time is equal to a 0.01 times the money in the account. So what this is really saying is, how fast is your money growing? It's growing at 1% of your original amount. So in other words, this is a very fast way to say you have a savings account that's paying you 1% interest. But they write it as a differential equation. And A at 0 equals 4,000. So this is saying when you put your money into the account, you put in $4,000. So then for this differential equation, solve for A. So like with example number 9, the example before last, I do need to get all of the A's on the left side and the T's on the right side. So I can divide both sides by A. That's going to cancel these. And that way I've got the A information on the left side. And then multiply both sides by dt. And then these dt's will cancel. So the left side has dA over A. And the right side, after these cancel, just has 0.01 and then the dt. So now that I've separated the variables, I could integrate on this side and integrate on this side. This is the same one that showed up many times. That's from the natural log. So that's going to be the natural log of A. The antiderivative of a dt, so basically the integral and the d will get rid of each other, and it just leaves you 0.01 times t, and then plus a constant. And like in example number 9, you can get rid of the natural log by using e. And these will cancel, and then a will equal, and then like I said, this, you could leave it like that, or you could rewrite it as e to the 0.01 t times e to the c. So this and this mean the same thing. And then the last part is plug in this information. So if you substitute that t is a 0, so put a 0 right here, then the a is going to equal 4,000, so put 4,000 on the left side. And right here, this becomes e to the 0, and e to the 0 is just a 1. So that means that 4,000 equals the e to the c. And I don't even need a calculator because that's basically just saying right here, put a 4,000. Because e to the c is equal to a 4,000. So just replace this with the 4,000. And because it's multiplication, you can switch the order. So you can actually put the 4,000 in front. So that's the traditional way to do it. And basically what we did is we created the PERT formula ourselves. So we proved where the PERT formula comes from.